Now, our first set of macromolecules would be carbohydrates. As you walk through carbohydrates, lipids, proteins, nucleic acids, it comes down to the real basics of biology, which is what do they look like? What is their structure? And how does that structure then impact their function? So you should be able to identify a macromolecule based on its chemical makeup. You then should be able to describe for me what function does this macromolecule serve within the cell. So let's start with carbohydrates. If you want to identify a carbohydrate, you're going to look at the components. You're going to look at the carbon, the hydrogen, and the oxygen. Now the ratios of these things are consistent. For a carbohydrate, specifically a monosaccharide, mono meaning a single sugar, you're going to see for every one carbon, there's going to be two hydrogens. And for every two hydrogens, there's going to be one oxygen. So you have this 1:2 to 1 ratio. Now you're going to see most of the carbon atoms in this molecule are linked to a hydrogen atom and a hydroxyl group. So lots of OHs. Sugars absolutely love water, right? They're very hydrophilic. Why? Because their chemical makeup, those abundant hydroxyl groups, are going to impact their ability to interact with water. So let's start monosaccharides. Here's an individual sugar subunit. This is the simplest level. Most sugars that we're going to find in nature are 5 to 6 carbons. We call these pentose sugars if they have 5. And if they have 6 carbons, they're hexose. Two examples we're going to see throughout the semester: ribose sugar, deoxyribose sugar. Both are used to help build nucleic acids. They're one of the components, are pentose sugars. Hexose sugars like glucose, C6H12O6, are used to generate ATP in the cell. Now it turns out there are different ways which we can view monosaccharides. They can take a ring form where it's cyclical, or we can have a linear straight chain form. Here's a nice example with glucose. See all of those hydroxyl groups we were talking about before? Also, we can easily identify that functional group. That's a carbonyl. How would you classify glucose? Is glucose an aldose or a ketose? You're right, it's an aldose because of that terminal hydrogen attached to the carbonyl. Here's the linear form, here's the ring form. We know there are symmetrical carbons here, which means that we can have an L form and a D form of glucose. Here's the first carbon. We can see here's the bridging oxygen in the ring form, and we number then to right of the oxygen, carbon 1, 2, 3, 4, 5, and then the 6th carbon is branched off that ring. So we have structural isomers for these monosaccharides. Glucose and galactose, same chemical formula, different structure. They can also be stereoisomers based on the position of that hydroxyl group. Whether that OH is above or below the ring, it's going to give us our alpha and beta forms. You can see the alpha form here based on the position of that hydroxyl. We also have mirror images based on those asymmetric carbons. So this is a D form of glucose. We would also have an L form of glucose as well. Hey, I just talked about it. Here it is. Here you can see the mirror image. Here's your D and your L. Notice here's our thumbs here. We can see if you were to flip and rotate this molecule, we have the positions that are going to be different. We're going to have different depths, making those enantiomers. Here we have our linear and our ring structures. Notice, in addition to having the linear and ring structures, we also have the beta and alpha versions, depending on where the hydroxyl is located. So those are monosaccharides. Now, if we link two monosaccharides together, we end up with disaccharides, joined by that simple dehydration reaction. The name of the covalent bond that links monosaccharides together is a glycosidic bond, very important. It's that glycosidic bond that enzymes tend to attack as we break down complex to simple. So for example, as you drink milk, the lactose, which is a disaccharide, is broken down in your gut by attacking the glycosidic bond. So here's an example. Here are two monosaccharides. Here's glucose and fructose. Here we can see then through a bridging oxygen, we form a glycosidic bond through a dehydration reaction. You can see here's the OH, here's the H that's going to contribute. Here is now the bridging oxygen that links the two together. We have now taken two monosaccharides and formed a disaccharide, commonly known as sucrose. Now the third type of carbohydrate is a polysaccharide, a complex carbohydrate. Many individual monosaccharides are linked together to form long polysaccharides, long polymers. There are two functions for polysaccharides within a cell. The most common function and the most popular function when you think what sugars do, they provide energy. Monosaccharides and disaccharides are immediately available for a cell. They're cheap forms of energy. Those polysaccharides aren't immediately burned. What they do is they're stored away, and during a time of need, we can slowly release individual units to use for energy. That's why simple sugars like sugary sodas, candies, etc. are not good sugars, whereas starches, etc. are better sugars for you because it's a controlled release. In addition to their role in energy, polysaccharides are structural in nature. They can form the cell walls, for example, in plants and fungi. So cellulose is fiber. Why is cellulose so difficult for most organisms to digest? I want you to think about that question as we go through. And then of course you can rewind and go back. So here's an example of starch and glycogen, two storage polysaccharides. Notice here the glycosidic bond that we see here in starch. Not only have our adjacent sugars linked through a 1,4 linkage, the first carbon and the fourth carbon, but we also have a 1,6 glycosidic bond, which the first carbon is able to attach to the sixth carbon, now giving us branches. Now what we do is we form layers. So this isn't just a long linear string, individual chain of sugars, monosaccharides. Now we can build off of that. So here we can see starch is what we would consider to be moderately branched. There are a few branches there. Glycogen, starch is storage form of sugar in plants. Glycogen is used in animals, stored in your liver. Here we can see 1,4 linkages, 1,6 linkages. Here's another 1,6 linkage. So now we have more and more branching, and understanding that each sugar here, each monosaccharide is a source of energy. That's what makes glycogen such a nice source of potential energy for our cells. Now here's cellulose. Cellulose is not digestible. This is what we consider to be fiber. Notice the difference here. If you look at starch and glycogen, notice the 1,4 glycosidic linkage is in the alpha form. The O is pointing down. But now in its beta form, with the O, what used to be OH pointed upwards, we have a beta glycosidic bond. Well, why that may not mean a lot to you on paper, the enzymes that digest alpha bonds do not digest beta forms of that bond. And so while we're easily able to release individual sugars because of our ability to recognize and to cleave 1,4 alpha linkages, we are unable to recognize the beta form, which makes this undigestible. So now if you were to ask yourself, here's molecule A, here's molecule B, which represents a carbohydrate? Is it A? Is it B? Are both forms of a carbohydrate? Are neither forms? Go again to pollev.com, put in your choice. Also, don't forget, also this poll, now that we've learned about cellulose, why is cellulose so difficult for most organisms to digest? Hopefully, the right answer is staring you in the face.